The first question I would like to ask you is to give us the highlights of your talk in a simple way, because it will be outreach.
The simple ways, the highlights of my talk is that I'm trying to live the dream of actually Pythagoras and Plato, try to geometrize not the cosmos like that, but the microcosmos, and try to see whether all the fields, including fermions, could match in a what's called a manifold, not manifold, but a super manifold, because the fermions are the electrons, what we are comprised. All the theories so far were abstract.
Spin one half, though.
Yeah, spin one half, but this is the particles that we're made of. So this program has been interrupted 40 years ago because they were not able to implement the fermions. Today I try to convince the audience that this obstacle has been removed, so we are close to, at least for myself, to realize the Plato's dream of geometrizing the microcosmos.
That's very nice, yeah. I will try to hear your talk, or at least to see your slides, because as you see, I'm very busy. The next thing we would like to ask you is to tell us your opinion about what we are doing. You have been here, I remember, as a student, so you have experience for so many years, and please let us know your opinion about what you are doing.
Yeah, I think when I came first here, I was a diploma student.
Diploma?
Yeah, 1985, I don't know, was one of the first or second conference, which did not take place here, but elsewhere. I think in the city center, close to the city center. And I was really astonished, actually, from the speakers and high-level speakers like Nobel laureates like Feldman, John Ellis, and other speakers. And yeah, this actually it was the reason that able to fulfill the dream of my life, try to become at least a good theorist in the first stage, and motivate me, of course, to embark on a career in theoretical research. More recently, I came here to this place, and recently I came to the Corfu 2 or 10, I think, and the change is remarkable. I mean, the place is actually the perfect place. It looked like Elysium fields, where people pursue their seminal work after they die and so on. But we can't do it before you go away. And this is actually the perfect place for this kind of conferences, and continues to attract all the major players on the field, not only the theory but also in the experiment as well. So it's a very comprehensive type of school.
Thank you very much. And what you will advise all these young people, you have seen several of them around, young researchers who make their first steps in the field, what will be your advice?
I advise them strongly to come to this, to attend that kind of conferences, to attend, and because they have the opportunity actually to speak with more senior people, to interact with them, something that I also had at that time, and I believe that's unique.
In a relaxed way.
In a relaxed way, and of course with all the social program that follows, accompanies this program. So it's really a comprehensive program on of social, not only scientific aspects, but also in social aspects, and that's exactly what is greatly valued. I should add here that's even more important, become even more important to me after these years of pandemic, which you can see the desire, people crave to come here and talk, communicate. I don't think you can everything replace with technology.
And we dare to do the meeting physically here.
It's actually, I should say, is the first after the pandemic hybrid conference that takes place. I am a member of international advisory committees. You know that SUSY 2014 went in Manchester, and Planck 2019 was the last conference before the pandemic, which also went in Manchester. And actually, we had very good distinguished speakers like Roger Penrose before his Nobel laureate. And this is the first one, actually, after this pandemic, and should be memorized for that. It's a very good, you need to be quite brave to do that, and I am really thankful to you.
We are brave.
You make it.
Right. So I'm going to give going to discuss an idea that bothers me, let's say, me and my PhD students for some quite some time, is the possibility whether you can geometrize not the cosmos but the microcosmos on a supermanifold using methods of differential geometry. And as you can see, and some of the ideas here was based on these papers, and some of the papers, the recent work that I'm going to emphasize is the inclusion of fermions in this setup. Right, so let's see. So the first thing is I will give some preliminary, some motivation for that. And I hope that will be proceedings. That's very important. And okay, it's good to the organizers. Actually, I like to say that produce proceedings for this conference. Then I will discuss about grand covariance in bound of gravity. Then I will discuss what the problem is. There was a problem that stopped this program compared to all other problems of geometrization, like string theory and other programs like the amplitude hadron and so on. And I try to convince you that you may well live, whether we can live with a supermanifold. I will try to see what the problem is and try to give present the grand covariant effective action, including fermions. Right, so let me start giving some motivation. I'm not going to go through all that. The only thing is just geometrizing the cosmos. It was actually many civilizations thought about that, tried to formalize in a more simple setting by Pythagoras and tried to put in the form of Platonic solids that our cosmos should be geometrized, not only the cosmos, the stars, the planets, but even there will be also the musical universalis and having some harmony compared to. So these ideas, of course, this developed. Okay, so what I'd like to show you here is how we go from cosmos to microcosmos. This idea was then later came into the debate between geocentric versus heliocentric system. Okay, and as you can see from Anaximander and Tycho, which is an hybrid system. Okay, and the heliocentric system with Copernicus, of course, who have the rigorous, so the explicit analysis of the heliocentric system. And finally, as we know now that both the Tycho's model and the model with the heliocentric is just a problem of choice of frames. One is a non-inertial frame, the other is an inertial frame. It will include fictitious forces we describe the cosmos. And finally, we had later the debate between the absolute and versus the relative local inertial frame gravitation. And this came to the conclusion again that you can have more freedom and using diffeomorphisms, okay, the symmetries of diffeomorphisms, and you can write even the microcosmos in a diffeomorphic invariant way and solve this kind of frame problem. Still, we still have some geometrization problems with the microcosmos, and this come from the quantum field theory and quantum gravity. We are living now in another age, which is the age of quantum physics. So let me see how, so the approach that I'm going to discuss, okay, let me first show what the problem is before we are going to how we will solve that. So the first one is that we have to old problem or recent problem within the quantum physics, whether the Einstein frame and the Jordan frame are equivalent formulations of quantum gravity. And of course, in the classical case, there is no problem. You can go from the Jordan frame to Einstein frame by making a filter parameterization. Okay, you can go in filter parameterization, you can have that. But when you quantize the theory, okay, the same parameterization you have done to go from one action to another does not work. Okay, you don't get automatically that the same parameterization of the background fields does not work. So the effective action is state dependent, except at extrema the action. Of course, this means you are calculating the S matrix amplitude, you are in particular extrema, or then you don't have, may not have this problem, but sometimes you need to calculate effective field theories, as we have seen in some talks. In this case, you have to worry about this frame dependence. You have to go calculate the delta rho electroweak observables, which are also offset quantities, which you also have to worry about frame dependence. And there is a big list, actually. You'd like to calculate bright bigness, resonances, which you need offset correlation functions. And last but not least, you need to calculate the inflationary potential at the quantum level, which also is frame dependent. So this is a partial list of reference, and this idea of the Mach's principle and device transformation of units. This is the context of this framework of this scalar tensor theory. It was from 1962, and there were a lot of papers, and I believe also that works of groups by Steinbeck discuss the question of quantum equivalence between the Jordan frame and the Einstein frame. And I believe we try to give now a solution to that using a covariant formula similar to the Einstein without assuming any new symmetries, no new particles, and no new extra dimension. We like to see how far we can go with these differential geometric methods. So what we should do? So that means there is an anomaly here, and the way to do that, we have to produce a new model function. That's what we did actually in 220. And the line element, the right element, should be G mu times L square phi. You could think about other things, becomes more complicated. But it should be a kind of measure that could divide out. And this dependence on the conformal transformation. So you can see all the model functions. Actually, these three, the last three, has been reported before in the literature, and this is the one which we included here. So the frame invariance of the classical action has exactly that form, and you can see that L should also be included in this action. However, why we don't worry about that in all this calculation? Because we can reparticularize L equal to 1, and you don't need to worry about that. But by changing the F case and the tildes, by changing the model for other model functions. But the path integral, you have the path integral measure. There is nothing there to absorb it. Okay, so there is an anomaly here, which will strike it back, and one. Right, so I will not discuss. So here I'll just give you an idea of how the effective action looks like. We have a determinant, which has this bar, which means you have to include this model function. Okay, it's different. So logarithmic the determinant is okay, trace of logarithm. And you can see here the one index is covariant, other is covariant. So this effective action, which is written explicitly, are covariant. And not only that, you find relation and equality that the effective action phi L F K A B is invariant. Okay, and the frame transformation transforms has this beautiful property, and the problem, the frame problem we had before, you can solve as long as you can deal with that to allow this perturbation theory. I mean, this is just perturbed one group, but this is a general result of effective action. That's my final part. Yeah. So you can now construct the effective action both for scalars and fermions. So here you have the path integral measure where phi q includes the gravitons, scalars, and fermions. Okay, could include, in that case here we have only scalars and fermions, we only mind the graviton. So this is the super determinant of G, of the metric, of the field space metric. So this is the action, and you see the source. How now, if you like to generalize that, it has to act right in this way. Right, so you can calculate, this is non-perturbative result, all orders. You can go to one or two loop case, you can expand that, you can see that one loop level, you get now the logarithm of the super determinant, which is equal to the super trace of the logarithm. That's what the super trace techniques, which discussed by Debes yesterday, and is applicable for SMET. But you can go beyond the one loop level, a two loop level, but you have to be very, very careful with the indices, the position, the fact that you have two flame covariant propagators, both on left-hand side, left and right. These are different propagators, but covariant. Both of them are covariant, okay? They are transforming, have the right transformation properties, and you can see all the indices are contracted, and what you see here, this is a fully grand covariant effective action. Grand means both field space and coordinate space, okay? That means covariant for space-time we already knew, but now we have a complete description both for scalars and fermions. Okay, so that's my conclusions. Right, so the conclusions is the first one is reformulation of the grand covariant action for scalar tensor theories with a complete set of model functions. This means that there is a new model function that determines the uniqueness. This question was asked in 84 by DeWitt of the VDW path integral measure, especially from the gravitational sector. And the line element should have exactly that form, so that both the line element and the effective action is invariant. So we derive rigorous algorithms for calculating the field space metric from the classical action for both bosons and fermions. The extension of the Vygotsky-DeWitt formulas on supermanifolds, so in order to include fermions, we need to extend the VDW formulas on supermanifolds. We have to geometrize on a supermanifold necessarily. And this opens the portal to discuss, or at least the chance, the great opportunity to discuss realistic theories such as the standard model. Okay? And finally, we have derived the grand covariant actions from the fermions. So the bottom line of this discussion is, yes, we may already live on a supermanifold, and that's the line element of field space metric. And this still need to do work to substantiate this claim, but for the moment, you can take it as a conjecture. Okay, thank you for your attendance.
What you will say is the highlight of your talk you gave here?
First of all, George, let me thank you for your kind invitation to come here again and to participate in this wonderful workshop. I'm really happy to be here, especially in this time towards the end, but still during the pandemic. So to see all these people, my colleagues, and especially young people who came here live, and active, it's a great inspiration for me to continue working in physics, to continue working for the benefit of academic sector, and I think it's a
you are vice rector, so you have high responsibilities.
Well, that's right, and that's what I can see here strengthens my will to work even harder for the common benefit. As for the physics, well, the topic I am touching in my presentation concerns known but not so far explored, phenomenon in the standard model and in models going slightly beyond the standard model, namely the existence of the high field strength vacuum, additional high field strength vacuum in the Higgs sector, which possibly makes our universe unstable, our universe, our life based on the electroweak vacuum as we know it from the accelerator experiments and from the established theory, which is known as the standard model. So there is this fascinating theoretical prediction that there exists a hidden world somewhere at very high field strengths, but probably still in the perturbative sector. And the question is whether you can get any message from that sector. So it looks like the only way to get traces of the phenomena related to the existence of that additional vacuum is to look for cosmological signals coming from the early epoch when the vacuum of the standard model got created.
Vacuum.
Yeah, precisely. That means another ground state around which physics, universe, could be locally built. So the point is that if we believe the common law at the beginning, in each causal disconnected sector, the vacuum was chosen at chance, was chosen independently from the choice made in the neighboring vacuum region, in the neighboring region of the universe. So between such places, between the regions where different choices were made, a transition region creates, which we call usually a domain wall. It's kind of a topological defect, and energy is stored in that transition region. And now, during the evolution, that energy could be released, and one of the channels, possibly observable, is the release of that energy in the form of the gravity waves. That's going to be a special signal which could be distinguished if we can measure it. So now the challenge was to predict the strength of the signal and the frequency of the signal, so that one could contemplate tasting that phenomenon at the current experiment. So that's what we did.
Thank you very much.
That's it.
The other question is what is your impression of what you are doing here? You have been several times. Now we have in the prospect of the new buildings.
I am truly impressed. I think it's a great job forwarding physics, high energy physics, and scientific culture in general. I mean, Corfu is a great place, so people can come here, they can get isolated from the daily business, they can concentrate on science, concentrate on their work, they can discuss physics in the great environment. And I think this is a really good idea to build here a permanent place which would house such kind of activities.
And the last question concerns you. You can see so many young guys being around,
Yes.
scientists. And what will be your advice to them?
Well, first of all, don't get discouraged by the pandemic. Don't get discouraged by anything like which is temporary, which we will pass over. You have to focus your mind on say far-reaching goals, far-reaching activities, and you should continue towards reaching ambitious goals of that kind. And that's I think the good strategy for the near future, and probably also for the somewhat further future.
Okay.
Here's the talk, and its title. Actually, I'm going to summarize in a number of slides work on unstable domain walls, which has been carried out in Warsaw over recent years, mostly with the effort of younger colleagues, Marek Lewicki, Paweł Olszewski, Tomek Krajewski,
Janek Kwapisz, Olga Czerwińska, Łukasz Nakonieczny. Those are the names which I'm obliged to mention. So the most recent work has been put on archive earlier this year, and that will be the final part of my presentation. So before I go to the actual topic of domain walls, let me give you some background. I mean, the model background or particle physics background which motivated us for these studies. So first, I shall talk for a while about standard model and beyond the standard model effective potentials with non-equivalent vacua. Then I shall discuss the issue of the domain walls as possible late traces of the early universe physics stemming from the existence of those non-equivalent vacua. Then I shall discuss the issue of the finite temperature corrections, and finally I shall talk about the possibility of observing gravitational wave signals generated by decaying domain wall networks. Now, let's move towards the domain walls. The crucial observable here is the energy density in various modes of the gravity signal produced by decaying domain walls. Essentially, technically speaking, the origin of this gravity signal is the time dependence of the energy momentum tensor describing the network, describing these walls. And it's, well, the expression is sort of complicated. The really complicated part is to implement properly the numerical simulation for each configuration generated on the lattice from given initial conditions, and then to run it through various stages of the evolution of the universe. That's the real challenge, and this is a painful experience and very painful calculation, even numerical calculation, even taking into account the possibilities, the unlimited, so to say, range of the present day computers. Now, one has to compute this energy density for various modes. K is the wave number, labeling various modes in the emitted radiation. Now you have to scale it to the present day. Well, I am using eta because it is conformal time which is used in all these simulations. It's a technicality. And the other important parameter here is the peak density. So A is the peak frequency. So the signal, as you will see in a second, has a special shape. It's a shape of which has a form of a certain peak, and the frequency of that corresponding to the position of that peak is a very important characteristic of the signal. So that's the parameter which tells you whether the signal can be observed or not in present day experiments. So that's essentially the basic formula which has to be implemented in numerical simulation to obtain a result in sort of realistic extension of the standard model. This is kind of theoretical prediction. So those are these predicted signals. This is one of the early papers on the issue from 2015, and you can see that theoretical prediction at that time was pretty promising. So it looked like the signal from decaying domain walls, networks of domain walls, could cut into the regions penetrated by current experiments. That's why it seemed to be worth checking numerically in detail whether this scenario is realized or not. Well, as you see, the answer is negative, but it is sort of interesting how it is reached. How does it compare to the possibilities of the actual experiments? Well, The experiments are here, the signal is here. So the frequency is much too high to be anywhere near the sensitivity of the current experiments. And of course, the strength of the signal seems to be too low. Now, what happens if you play with new physics represented by these operators I was mentioning before? Here are various examples of the network evolution. So this is essentially, those plots show you what is the portion of the lattice space occupied by the electroweak vacuum. So you can see that by small changes in initial conditions or in the scale or in the lambda 6, you can, in the value of the lambda 6, you can obtain very different solutions. So this one is preferred because you end up in the electroweak vacuum. These two are essentially disastrous. So those are options which you have, which you will examine, changing various parameters in that correction to the standard model potential. Well, here what you can obtain, maybe the next picture is more telling. Somehow this is the standard model case, which I was discussing before. Here are the best signals which we have obtained by playing with the, well, within reasonable limits, with this correction lambda 6 phi to the 6. So you can see that we were able to gain a bit, to go to somewhat towards lower frequencies. Here is the peak of the modified signal, and we were able to get up in the energy, but it's not a big. It's still, we are nowhere near the sensitivity of the current and future experiments. So the way we were able to raise the strength of the signal and to lower the frequency was to play with this additional piece of the potential in such a way that you make the difference between the energy of the two vacua smaller and smaller. You cannot make it too small because then you lose you lose the power of your simulation for various technical reasons. So that looks like a large number, but that's the smallest possible difference between the vacua which we were able to follow during the simulation. Now, into this analytic formulae. This way we're able to obtain such a plot. Well, here is the prediction of the positions of the peak of the signal of the domain walls on domain wall network from the reasonable extensions of the standard model. So essentially, the parameters are taken in such a way that the previously obtained spectra are located somewhere near this strip. Still, it looks like the strip is very far from the region where the signal could be observed. So it looks like maybe there is some physics, from exotic physics coming from the early universe, but we have to devise an interesting and ingenious scenario to have the access to that physics. So that's the situation for today. Thank you very much for your attention.
What will be the highlight of what you are going to present?
We are working with Hermann Nicolai for many years. So he was the director of the Max Planck Institute in Potsdam, in Germany. So we are working for many years.
Albert Einstein Institute.
Albert Einstein Institute, yes, exactly. For many years on the so-called conformal standard model. We have proposed the model even before the LHC started. and we assume that there is no supersymmetry, which at that time was the most popular symmetry. Everybody was expecting that LHC starts and there will be ZNOs, VNOs, selectrons, and squarks. It didn't happen. We predicted that, in a sense, in 2007, several years before, replacing supersymmetry by conformal symmetry. And this replacement leads to many, many predictions that we still wait, in a sense. One of them is the brother of the Higgs, the heavier Higgs. That's one of the predictions that has not been seen yet in LHC, but we are waiting. So that is one part of my talk will be around about the conformal standard model. The other one is the top-down approach, namely we proposed in a sense the prediction coming from the E10 symmetry. That's a huge symmetry, largely unknown in mathematics. There are no representation theory. Not much is known, while one thing is predicted by the theory, namely the presence of 8 gravitinos. That there are SU8 there. And the 8 gravitinos in the framework of SU8 is very interesting because Murray Gell-Mann, that recently passed away, proposed that from SU8 one can predict the number of generations, that there are 6 quarks and 6 leptons, no more, no less. So that's very interesting as a prediction. So that's something that I will talk about in a sense, in what sense this prediction is there. I will not talk about my collaboration with Roger Penrose that lasts for 10 years about the eons. But next time, I hope next year, I will talk about my
gravitinos sound like supersymmetry. So
yes, but it's only the field content. It's only the field content, but not the interactions. There is no supersymmetry as such in the model.
Unfortunately, we cannot discuss more on that.
Yes.
So the next question is, what is your impression of what we are doing here? I mean, you have been also in the concert the other day.
Yes, I was.
And you know what we do.
Yes, I've been here before. I love this place. Absolutely.
Boat trips, and we will have also these buildings renovated
yes.
soon.
Yes.
And you will have office space there.
Yes. Thank you. Yeah.
So, what is your impression about that?
I was here in Corfu before, and I love this place. That's why I returned with much pleasure after this pandemic restrictions. I hoped to be here last year, but it was not possible. So I'm looking forward to coming here, possibly every year, because there's a very nice atmosphere, surroundings are beautiful, very good physicists come here to talk. Now part of them in a hybrid way, unfortunately, but let's hope that next year everybody will be present.
Will be here,
Yes, in person. That's what I'm looking forward. So it's a very, very nice, it lasts 40 years already. So it's a very nice place with very good atmosphere, nice surroundings. So I'm looking forward to coming here in the future.
Very good. And what about the young researchers? What is your advice? You see around so many. Some of them they come from Warsaw, actually.
Yes, they do. Some of them were my PhD students. So the situation in particle physics is on one hand difficult because there were no new discoveries by LHC up to now. So it's very difficult. After the Higgs, yes, the Higgs was part of the standard model. So in a sense that was expected by theoreticians. So on one hand it's difficult because there is no, in a sense, pointing toward where should we look. Because we know, on the other hand, we know that the standard model is not the last word. Yes, because it has its limitations. It doesn't predict, for example, the matter-antimatter asymmetry in the universe. Many things are not, in a sense, predicted by the standard model, although the structure of masses is just measured and not. So there is a lot to do. So even without this experimental hints that we don't have yet, there are many theoretical ideas, but up to now they have to be decided by the elegance and beauty and simplicity.
We follow our
our intuition and taste and everything. So that is important in a sense, because we know that physics is not done yet. So therefore, young people will have a very difficult task ahead of them, much more difficult than we had, for example, when the new discoveries were along the way. But in a sense, it is even more exciting in a sense, since we know a lot about the Standard Model, we know a lot about the cosmology, and we know that they do not match, first of all, and second, of course, the Holy Grail is connecting gravity with the particle physics,
which is not there yet.
Which is not there yet. So it is exciting, also extremely difficult. So, but being a young scientist that I'm not now, I would go this way as I did 40 years ago.
My talk was about the new symmetry, in a sense, incorporating gravity into the particle physics. That's E10 symmetry. But since the meeting is devoted to the Standard Model and beyond, I will start from the conformal Standard Model that we proposed with Hermann Nicolai 14 years ago, before the LHC started. I would like to emphasize. So we assume that there is no low energy supersymmetry, that the low energy supersymmetry is replaced by conformal symmetry, and that's the model that I would like to say a few words about. So we assume that there are no new scales below Planck mass. There is a grand desert beyond the weak scale. The cutoff is a bona fide physical scale. So we don't hide the problem of the quadratic divergences within the dimensional regularization, because it's only hiding the problem and not really solving the problem. The model should be viable up to lambda. The vacuum should be stable. We know that in the Standard Model it isn't. There are no Landau poles up to the Planck scale. That the model is defined at lambda at the Planck scale, and it is renormalizable there, and require vanishing of quadratic divergences. That gives us two more constraints it is important. And the seesaw mechanism for neutrinos, so we have right chiral neutrinos, of course, and B minus L is broken spontaneously by but explicitly only by gravity. And that's another requirement, that it explains the observed baryon to photon ratio. We know that the Standard Model with its CP breaking is not explaining the baryon to photon ratio. This number would be 10 to the minus 14 for the Standard Model, and we know that it is 10 to the minus 10 because we have a new source of CP breaking. So the model itself, I just flash it to show that it has only a few more parameters. The yellow ones are new ones with respect to the Standard Model. The white ones is just the Standard Model. We introduce a new complex field that couples to Majorana coupling to the right chiral neutrinos. And the last term is assumed gravitational breaking of order 1 over Planck mass squared. It has only a few more parameters on top of the Standard Model. So the Standard Model has only weak scale neutrinos, these right chiral mostly neutrinos, complex new scalar phi. The real part of phi couples to phi through the mixing. So the actually 125 GeV, what was measured at LHC in this model, is a mixture of mostly doublet and a little bit of this new one. There should be another orthogonal combination that would be mostly new one and a little bit of the doublet. And that's the way both are mixtures. So, and we can predict, in a sense, when the mixing angle is given, we can predict the mass. We don't have a mass of the new one, but we are waiting for the new Higgs-like particle, but very narrow, because the mixture of doublet is very small. So the phase of phi couples to Standard Model only through the Y nu, the Yukawa coupling, and mass is from assumed gravitational braking. So it is axiom-like particle. So there is broad angular Higgs mechanism for electroweak symmetry braking and spontaneous symmetry braking for lepton number symmetry, because this new field has charge number, has lepton charge -2, because it couples in a Majorana-like way to right chiral neutrinos. So it couples spontaneously lepton number. And of course, the seesaw mechanism for neutrinos. We assume that the scale is of the order of the weak scale, but the coupling is very small. This y nu is very small. So we have masses of neutrinos from the seesaw. So it is not a large scale and coupling of order 1 that is usually assumed for the seesaw mechanism. We have coupling, the Dirac coupling is of order 1, the Ym is of order 1, but the coupling to right chiral neutrinos is very small. So that makes the mass small. And that assumption, y nu is very small, makes all the precision tests of LEP viable, because the new sector doesn't couple to the standard model, or couples very, very weak. Okay, so SM is unchanged in the usual sectors. That's what I already said. Only a couple of new parameters. I recall that minimal standard model had 115 new parameters. It turns out that the vacuum is stable. We checked that there is no going underwater, about 10 to the 10 GeV, usually for the standard model. It goes up to the Planck scale above 0, the self-coupling. All couplings can be small. If we start them small, they do not run. A set of new particles is the right chiral neutrinos. We always have them with the seesaw mechanism. They are very weakly coupled to the standard model. One scalar around 1 TeV, but mass depends on the mixing with the doublet. So mixing with the usual Higgs. So phase of new scalar field is very light and extremely weakly coupled. So it's an axiom-like particle. Hierarchy problem. And now I come to these two additional equations that we impose. So in essence, they are not seen in dimensional regularization. As I said, it hides the problem of quadratic divergence, because we then have to go to 2 dimensions to see them. But in 4 dimensions, we see only logarithmic divergences by the dimensional regularization. So when we calculated treating lambda as a bona fide bare physical scale, so we impose the coefficient in front of the, because the only 2 parameters that break, that are a problem in the standard model, there is 1 parameter, m squared doubled Higgs doublet squared. That's the only parameter that breaks conformal symmetry that has quadratic divergences. Now we have 2 scalars, so we have 2 such parameters. So we calculate the coefficient in front of m squared, or in front of the quadratic divergence, and we impose them to be equal to 0 at the Planck scale. But it turns out gravitational corrections turn out to be small. That was shown in this paper before. But it turns out that once we impose them at the Planck scale, they are valid all along. So once we impose that there are no quadratic divergences at 1 scale, there are no quadratic divergences at any scale. So they run in a sense together. Okay, so when we impose these conditions and we add the baryon to photon ratio that we want to explain 10 to the minus 10, then we have a set of 3 equations and we have 4 new scalar couplings. So in a sense, it's almost fixed. If the new Higgs, the partner of the Higgs, was discovered, so we knew the mass and the mixing angle, then all 4 of them, all 4 new couplings would be fixed uniquely. And then the model could be falsified fully. There are other, discovery of the new Higgs-like scalar will make it unique. Okay, so E10 symmetry. It was noticed by Kremer and Gilliat at the end of the 70s that n equals 8 supergravity, that can be understood as a compactification of 11-dimensional n equals 1 supergravity to 4 dimensions, exhibits global E7 symmetry. Normally one would expect SU8. We have 8 charges that we can rotate any way we like, but it's bigger, it's E7. And actually they noticed that if the local SU2, which has 63 adjoint representation. When we add 70 scalars, we have 133, and it's the adjoint representation of E7. And they actually realized this E7 as a global symmetry on n equals 8 supergravity. So that was a huge surprise that the symmetry is much bigger than just follows from naive rotation of supergravity charges. Okay, so going further, if we go down to d equal 1, so that's from 11 to 4, we have E7. So we expect going from 11 to 1, when we have only time component, it should be E10. So, and what is the reasoning? In the early universe, the time coordinate was the most important one, because no one knew its neighbors. Yes, because when we are at the beginning on the Penrose diagram, we go up, in a sense, vertically up. So in a sense, we don't know we cannot build a field at the beginning, spatial part of the field. So that's the idea. So we expect E10. Then we can write a Dynkin diagram for E10. Since we know we have the classification of compact Lie groups, and E8 is the biggest one, that is a different thing. The full representation of such involutory or maximal compact subalgebras, it is hyperbolic, is unknown. Mathematics of this is largely unknown of these. For n bigger than 8, they do not belong to any standard class. For smaller n, we know that, for example, this involutory K of A7 is SU8 and K of E8 is spin 16 over C2. But we have E10. So n equals 8 supergravity, as I again flashed the field content, that points to an infinite symmetry group E10, and it's really infinite. Infinite and infinite can be different. This is really horrendously infinite group. Of course, the number of generators is infinite. It exponentially grows with the level, and that's a horrendous thing in a sense mathematically. But it unifies gravity with all the other interactions in a very different way from any GATT or string scenario. I spent 17 years on string theory, so I really can say that it's very, very different. So, but since the mathematics is largely unknown, we have to dig out some information from this E10. And one observation is that after breaking all supersymmetries, we don't assume any supersymmetry below the Planck scale. The theory is completely non-supersymmetric. It has exactly 48 degrees, massless degrees of freedom, fermion degrees of freedom, as in the standard model with 6 quarks. So Murray-Gell-Mann noticed that, and that can be an explanation of 3 generations. There cannot be more, and there cannot be less than 3 generations, 6 quarks and 6 leptons. Murray-Gell-Mann had a problem with assigning the charges, because quarks and leptons, they are okay, that they are 3 triplets and so on, but and electromagnetic charges turned out to be different by 1/6. For example, electron has -5/6, neutrino has 1/6, and so on. So that was a problem that Gell-Mann noticed. And when the symmetry is broken, that's what Gell-Mann did, it requires a very natural deformation of the coproduct, and all 1/6 go into place. So electron has charge -1, neutrino has 0, up quark has +2/3, down quark has -1/3. Everything fits into place with a very natural deformation of the coproduct. So it is not part of the gauge symmetry. It belongs to E10 and not to gauge symmetry SU8. Okay, SU2 plays a very different role than SU3 color times U1 electromagnetic. So normally we expect that when we go up above 100 GeV, SU2 will be more and more visible, will be more and more exact. While at the low level, in this room, for example, we see quote unquote SU3 color. Of course, there are condensates, of course, so we don't see that exactly, and U1 electromagnetic. SU2 is not realized at low energy. In this picture, SU2 is never realized exactly. It's an approximate symmetry up to the Planck scale. So, and K of E10, that's a very important thing, predicts the existence of very heavy, fractionally charged, electromagnetically stable and strongly interacting gravitinos. So let's go to the summary. Conformal standard model has definite unique predictions for LHC. Beside the Higgs particle, one Higgs-like very narrow heavier scalar. If it is discovered, we can fix all the couplings and we can see whether it fits what we predict. Right chiral neutrinos are too weakly coupled to be visible. The prediction is almost unique, full unique test would come with the discovery of a new Higgs-like scalar. That's why I'm very much waiting for what LHC will see after starting in March. This infinite group going bottom up, well, on top bottom, infinite group is broken at the Planck scale and it provides a completely novel unification of all forces. One of the predictions is that 6 and only 6 quarks. If LHC sees any fermion of spin 1/2, the whole thing is over. The whole thing is gone. It predicts only those fermions that we see, that we have seen as the only fermions of spin 1/2. There are also 8 fractionally charged, stable, strongly and electromagnetic interacting Planck mass gravitinos. Being extremely massive and therefore very diluted, they can be candidates for dark matter even though they are charged. Their annihilation in neutron stars can explain the origin of ultra-high energy cosmic rays, in fact nuclei, observed on Earth. And their clumping in the very early universe can also explain the origin of observed giant black holes. Time will tell. Thank you.
And I would like to tell us first in simple words what are the highlights of your talk, what you will present here.
Yeah,
in an understandable way.
Yeah, I'm probably a strange person in that I like to go against the obvious things, and I will give that as an advice to the students actually later. So, if we look in the mirror, what we see in the mirror looks feasible. It takes a while. If we don't know that the person is left-handed or right-handed, we cannot say if it's in the mirror or it's just a very, very clear window, right? So that means that in mechanics, usually left and right are exchangeable and we have a symmetry. Basically, we cannot do it. We cannot say it. Another thing, if we still in mechanics, no heat produced, if we have a pendulum going back and forth, and we film it and show the film backwards, once again we cannot see the difference. And that's true for all long distance forces. And we thought for a long time that it was true for everything. Mm-hmm. And then around the 50s we realized that it was not true, and in some small cases
Pauli made even a theorem out of that, right?
Yeah, but at some moment when we went to the 50s, people realized in some cases things that you see in the mirror could not be realized as a real experiment. Sure. That means that fundamentally, this is the famous experiment of Mrs. Wu, this is fundamentally the building blocks of our theory, what has become now the standard model, is the mainstream, were not symmetrical between left and right. Okay, and that was anecdotic for a long time. And then came the standard model in the 70s, and we realized that indeed all the building blocks were not slightly but maximally asymmetric. And when you look at particles in the very close distance, for most of them, it's maximally violated. The left-handed particle interact, the right-handed particle don't interact. My question in the talk is, since everything is so broken between left and right at short distances, how comes we have been fooled for so long by the fact that long distance, all the interactions which persist at long distance respect the symmetry between left and right. And so that's why I tell you that I like to go in reverse of the.
And the rest, if they're interested on the answer, on the why, they should hear your talk, which also
The talk will be accessible to last year students, last master students.
Very good. What is your impression in general about what we are doing, the progress of the whole thing, taking into account also that we renovate the buildings that will be office space from next year, all these buildings and so on.
Oh, I was wondering about the construction going on. I was afraid. I was afraid it had been bought by some promoter.
Well, we had difficulties to push it to go on, but anyway, it goes on. Yeah.
Okay. No, but you kept this wonderful park, and well, the office facilities we'll see later. That would be nice to have close by, because that means that once the sessions are over, people don't scatter in town, and the students have an occasion, a place to meet the visitors. Now, as to the meeting, well, you know my reference is Morion, and you know it because we shared a room in a very long time ago in one of the Morion meetings,
that's true,
and that's the amount of interaction. So we have this potential for interaction here, not only between old friends, but with young students. If a student comes up to you, you just treat him, her, excuse me, as an old friend, and that's the same thing. They shouldn't be shy about asking. So that's very important. It's very difficult to maintain when you have the remote system, and we have had the problem with Morion. We did something successful.
What did you do this year?
Well, for Morion Electric, we did something successful, but I'm ashamed of it, if you wish, because it became technical. What we did was to ask the speakers to give their talk the day before the date. And so we had the talks and slides available on the net for 24 hours.
Nobody was in person there, right?
Nobody was in person. We had that for 24 hours. And then we
we are brave enough.
Brave enough. But this was a few months ago. And fortunately, this is why I jumped to come here, right? I was so eager to come. And but then what we did was that people would ask questions, and we have a live session of 2 hours. So people from everywhere in the world could join in the session.
That's a good idea.
Yeah, but the problem, I don't advise it. The problem was that with this preparation, the questions became highly technical and specialist, and I think a young student would not have dared to ask a question. So, if you want, it was successful for once, and a good reason not to repeat the experience.
I heard a little bit of that in the string conference. I cannot say it was sensitive. It was for experts. And given that, what will be your advice for the young people who are here?
Well, for
you
those
have a
who
lot of experience.
For those who are here, this is already okay. They've already won the situation. The first advice for those who are not here would be to participate in live meetings, in person, and not play the game of the famous, I would not call it nationality, but somewhere in the Americas, a professor who comes for just 55 minutes before his talk and her talk, and lives just after his or her talk. No, that's really, like in Morion, we insist that people stay, well, not necessarily for 2 weeks here, but for a few days, so that they attend live meetings, that they shouldn't be afraid to ask questions, and especially that they don't believe what they are told. Or training in science, when we hear something, is to wonder, is this true? Or
what is the truth behind it?
Yeah, or would the opposite be true too? I mean, it's really, you need to question all the time. Not up to the point that you cannot do anything. And then when you do something, well, at some moment you should go through it and not question it every line, because otherwise you will not write the second one. So this is a very, very simple talk. It's more
a reflection of thoughts, and of course, I will not answer the question. I don't have an answer. There is maybe one thing for us humans is we are trained to look for patterns. For example, as soon as some panorama of the planet Mars comes around, people start seeing human faces in it. So we have some kind of automatic search for some patterns, which of course leads to some bias. And we may wonder whether the searching for symmetry is sometimes such a bias. We may be looking for symmetries where they don't exist. Of course, here, if you see a catamaran boat, you try to align with it and you align with the sun, and the result starts looking symmetrical, of course, because you walked just enough to get it symmetrical. Well, this is a joke. I'm trying to use some pictures from here to make it more okay. So the thing is that when we know the answer from the standard model, parity violation is the default expectation. When you start with the standard model, it's completely a chiral model, and we should not expect to have parity restoration. Still, over the centuries, we have lived with the idea that the world was symmetric between left and right. Not that it is symmetric between left and right, but that it should be symmetrical between left and right. We have seen left-handed and right-handed people, but you thought, okay, well, this is a bit quirky, but that's life. There is a majority of right-handed people. Strange, okay? All those people have left-handed DNA, but okay, so what? Probably the first DNA was left-handed. So basically, we have moved to, which we always do in physics, to the idea that the rules themselves are symmetrical and that the boundary conditions are violating them. And since we are not supposed to predict the boundary conditions, then life is good. So it's reassuring. And in fact, when we looked beyond, I would say, human beings, well, living beings and so on, we saw that in all practical experiments you can do on Earth, basically left and right are equivalent. I don't mention the Earth rotation effects in this. I mean, okay. When we do an experiment, we look at it in the mirror, and the experiment we see in the mirror is realizable. We have no way to tell it's not a physics experiment. The same is true to a large extent for time reversal. If we film a mechanics process, of course, it's reversible as long as we don't get entropy in it, aging, or heat dissipation. At long distances, parity seems restored. We have already said it. And it looks like nature has been doing everything to fool us into thinking that parity was respected. And that it took strange machines like Wu's experiment to prove the contrary. Actually, yes. And why? Why is it so? If we take SU5, well, all the fermions, you can put them all in left-handed multiplets. Certainly the 5 has only one chirality. Okay, so it is broken. But we still emerge with a vector-like coupling to the photon and a vector-like coupling to the gluons. I would consider the gluon interaction to be long distance. It's long distance with respect to the W and Z. One possibility to explain that, I'm trying to find reasons, is that in the models that we are using, we need to have anomaly cancellation. And that's certainly one criterion. And since we have been living with relatively low representations of the groups, we cannot build we cannot couple the photon or the SU3 in a way which is not parity invariant. For SU3, for example, we find 3 and 3 bars, and we never find the 6 in the lowest lying in the representations of SU5 which are used. So I didn't do, certainly I didn't do comprehensive studies of anomalies in those cases, because the whole point is in the usual representations, you end up with only 3 and 3 bars as like particles, and therefore SU3 would be parity respecting. Now, of course, there is one answer, is that the reason why we have parity conservation in long distance forces is that long distance forces are gauge invariant, remain gauge invariant. That's why they are long distance, because the photon is massless, and let's say that the gluon is massless. And as soon as as soon as I have a mass term here, this mass term may result from some broad angular Higgs breaking, or it can be a genuine mass term. This, at this stage, behaves as a number. If I do a phase transformation, a gauge transformation, alpha left phi, alpha right phi, but you see there is only one solution, that alpha left has to be equal to alpha right, which in practice means that the gauge charges of the left and right-handed fermions have to be equal. So at this point, the question becomes that basically, let me just go back, basically the reason we would have that parity is restored at long distances, this is true for the U1 electromagnetic, this is true for SU3, the reason would be that we only have massive fermions to be charged. The neutrinos are not responding to directly, not directly coupled to the photon or to the gluon. And as long as we have only massive particles to be charged, which is a very old hypothesis that all charged particles have to be massive, then we would have long distance parity conservation. Well, this is not an answer from fundamental laws. This is an answer from the fact that the zoology, I have more than enough. The point is that the zoology of the particles we have does not include any charged massless particle, okay, for some reason. So once again, don't blame the fundamental forces, blame the zoology, the boundary conditions. Well, we may wonder, we want to go further, if it would be possible to have massless, I have to beware of that speaker in my back, whether we could have massless particles which are charged. For example, you can think of a light, very light electron, left-handed, emitting a photon, which is polarized, fully polarized left or right. And of course, this would lead to a right-handed electron. And if you do that forward, you indeed get a linear divergence in this, which means that the massless limit is really a problem. And it's a problem because, in a way, as soon as you have a small mass, you have an E right, but if you have a zero mass, you don't need to have an E right. So it's a bit funny thing. Actually, this was looked a lot at, not a lot, but it was looked at the start of HERA, because there was a fear that this would be a background for right-handed currents. And actually, the limits can be reconciled. There was a controversy. I tried to download some of the papers. I only downloaded one. There was a controversy for a while, but the idea is that, let me just, sorry, okay. The idea, if you want to solve that limit, is that you are not allowed to speak of a beam of left-handed electrons if they are massless. It will always be degenerate with a right-handed electron with a photon parallel to it, a soft photon. So in a way, you have to do something like the PDF treatment that is used in QCD for those collinear anomalies. So, okay, it seems to be just a feat of nature that it has chosen not to have massless particles, and that leaves us with the interrogation of why parity is conserved.